Today, I would like to talk about medical AI agents, which, if you look at the title, sounds a bit more like session 2 topic. But I think there was some overflow, so I'm kind of taking over some part of session 4, but I hope you don't mind. So a little bit about myself. I actually started out in Basel in medicine, did some medical studies, and then pivoted into machine learning for my PhD, and then left completely into machine learning and AI, left to that world, and now came back for starting my own group, the Medical AI Lab, which is located in Basel, but part of ETH Zurich's Department of Biosystems, Science and Engineering. So today I would like to talk about how AI is permeating our everyday lives. And I hope that we can actually change the way healthcare is operating thanks to it. And this could, for instance, mean we can have better systems to integrate different types of data, earlier and more comprehensive diagnostics, but also more personalized targeted therapies. We cannot tackle everything at once, but one thing I want to mention here is that conventionally, so in the last 10, 20 years, there has been lots of efforts in developing machine learning and AI methods or models for healthcare applications. And the big problem with those was typically that they were developed for a very fixed and narrow data modality. I'm also guilty of that myself. You know, for instance, you take some time series data set of patients and you try to predict a very specific onset of a disease. But the problem is those models are very narrow. So if you try to deploy them, then everything will fail because there is some kind of train test distribution shift. And finally, another big problem is that many machine learning and AI models are historically very black box. So we don't really know what is happening, which is a great problem in healthcare, where most disciplines where you want to know exactly why a specific decision was made, except for anesthesia, where nobody really knows how those drugs works. So how do we fix this? Regarding the data modality, I believe we need to move into a new direction where we have models that are much more flexible, that can ingest and produce very different types of heterogeneous data modalities. It looks easy, but it's actually quite hard. We need models that are more adaptable. That means they're not just multitasking models, but they're models that can adapt at test time, at inference time, to new problems, to new tasks that they have never seen before. And finally, I think we need to venture into a world where models are actually able to reason with everything we know about medicine, biomedicine, all the knowledge out there that humanity has built up over the millennia. So this rough vision, I have, with some other colleagues, written down a few years ago. And since then, actually a new point has entered, namely with the rise of language models, we have the big problem that many outputs that those language models produce are confabulated or are not really verified. So how can we build models that are also grounded in actual guidelines, in authoritative knowledge sources that we have, and how do we verify this in a non-verifiable domain? Well, the medical domain, I believe, is actually very complex for AI, because you can have a simple problem, a patient walking into the emergency room and presenting an unspecific symptom like abdominal pain. But the problem is there is a myriad of different differential diagnoses that might be hiding behind this. And for many of those, you might need a completely different type of workup. So conventional machine learning models and now language models that are being trained on exam-style problems where you have a case and then you have a question, you have an answer, they don't really learn by design how to explore the environment and how to seek information. This is actually much harder. In an early work that we released roughly 1.5 years ago, which we call Agent Clinic, we showed that if you take those exam-style benchmarks that have been widely used, where big companies like Google are showing, hey, we are doing really well on the USMLE exam, we showed if you actually take this exact benchmark and convert it into a dynamic benchmark where doctor agents have to talk to patient agents, etc., many of the performances drop drastically. So that was quite some time ago already, but interestingly enough, last week, I talked with ChatGPT about some agent benchmark thing, and at some point it out of nowhere brought up Agent Clinic and said, hey, no, this is actually one of the best existing environments for evaluating AI agents. Why? Because it models a doctor agent, the patient agent. It was kind of doing a pitch, and I was like, this is so weird. I was kind of, surprised by that. So there is an unexpected fan somewhere out there. Okay, so I just dropped the buzzword of an agent, but what is it exactly? I think many of us are quite familiar with the concept of language models. We use them every day, or many of us, I think. But what is a language agent? So the language model basically is just a question answering machine, if you want. You take in some input prompt and it produces a sequence of words, for instance, could be an answer. And the language agent is actually a much more complex system. You have an entire environment where an agent might use different types of tools. It could be a calculator, different types of databases that only you in your hospital or in your company have access to. It could use web search and various other things. It still has to solve a specific task that a user requests, but then the task might not be completed by just returning the answer, but it might be completed by returning an answer and actually executing those tasks. So an agent is all about taking actions in some sort of environment. So 2 years later, doing now a jump, roughly, at the start of this year, we saw something quite astonishing. There was a massive surge in the public's interest in AI agents. Some of the earlier works of language agents we have been working on in 2024, 2023, but now all of a sudden this got really, really hyped by some open source frameworks that many people have been using. So this shows the GitHub stars for one of the most famous frameworks called OpenClaw. And maybe if you're not familiar with GitHub stars that the project gets, this number is very significant. The most heavily used machine learning library, PyTorch, only achieved 100,000 stars after many years of being the de facto library that everybody used. And somehow, OpenClaw gained a community of over 300,000 stars within the shortest period. So I think this is really new. So there is a surge of interest in agents and their capabilities. We're going from early development into productive environments, but we're going too fast. So maybe some of you have seen how people have been deploying agents, and some of them have used agents to handle their emails, and that might have led to an accidental deletion of the entire inbox, which I think is great because it's really hard to get to inbox 0. But nevertheless, we actually need to worry much more about the reliability rather than just unlocking new capabilities. I feel 2 years, 3 years ago, it was much more the time, how can we get new capabilities into a model? And now it's much more, how can we get a model reliable? Because it can do all the things. We can hook it up to your Slack. We can hook it up to Google Docs. We can hook it up to your credit card. We can hook it up to everything. But how do we actually align it to your values? How do we make sure that it's actually following through with what you need? So this is exactly where our lab's research is actually centered around right now. So we want to develop and also evaluate flexible medical foundation models, but also reliable AI agents that are grounded in the multimodal riches and biomedical knowledge that is already out there, and hopefully build new knowledge this way. So just very high-level topics that we research. It's basically the language model layer, then of course how we can build agents with them. And concretely, we also study how we can benchmark those capabilities and how we can connect language models and language agents with various external information sources. And ultimately, of course, the goal is to develop an agent that kind of joins both the patient side with the knowledge side to then have a much more personalized N=1 study that is basically being run on a single patient. So to give you a very brief overview of some research activities from our very young lab that now has been running with a small batch of PhD students and master students over the last roughly 1.5-ish years. So we have been focusing a lot on how we can develop better medical language models, specifically reasoning models, and how we can position and organize medical knowledge around language models such that they are better at retrieving the right piece of information. We have been also focusing on multimodal language models and how we can actually develop systems such that a language model can talk about specific images, for instance. And a really big cornerstone of our research in the last year or two has been pushing really the agent frontier, which includes also various applications. So there is like one project going into oncology agent direction, where last year we presented the first molecular tumor board benchmark at NeurIPS. There's also a very new rat agent preprint that just came out a few weeks back, where we have a radiology agent that uses various tools to process volumetric images. And then there's all sorts of other adjacent agent research and how can we actually use agents to do science on their own, and how can we improve the way we train language agents. Because just using agents as inference time has become quite easy, but actually training them in a way that they learn how to exploit their environment and how to get better at the tasks they're being tasked to do is actually not so trivial. So there's lots of exciting research going on there too. But today, I want to focus on a few of those sub-projects and talk a bit more about those. So one question that I think is very important for the field right now is how can we make agents more reliable? This is especially important in the medical domain, where we cannot afford to have an AI assistant that says, when you ask, is this mushroom poisonous? And you say, and the agent says, well, no. And then you are sick. And then it says, oh, let me tell you more about poisonous mushrooms. So we don't want that. And the second question that I want to briefly mention here is there's some really exciting development in actually agents allowing us to unlock language models that have faithfulness. This is a big property that we have been missing for many years. And in one application, we can talk about this. But first, how do we make agents reliable? This is a really big question, and it's impossible to talk. You could fill an entire 2-hour session just about that. Today, I want just to briefly mention two approaches. One is how do we properly ground a language model in external knowledge? And the second one is how do we supervise individual steps that a language model is taking? Okay, so on the grounding, so just to repeat what a language model and a language agent does, there are two different things. So on the right side, you see the language agent, and it's typically needs some kind of language backbone that is put in some sort of environment where it has access to different tools. All of those tools, it might use the right or the wrong way. So there might be lots of failures and so on. And here you only see this little database, but in the medical context, that might be actually a very complex question. What type of knowledge do you surface to your AI agent, and how do you best do it? So one thing that many people have been doing over the last 3 to 4 years with language models is they just say, all the knowledge we have, we put in a large database, and then the language model has to search a database that contains millions of documents. And we just retrieve, for instance, using vector search, the most relevant documents, and we add it to our prompt, and then the language model has been informed by the maybe most relevant guidelines, the most relevant textbook, the most relevant trial that has been run for this very specific question. And this is what people have been doing. But the big problem is that this database of documents under the hood is just a large pile of Lego pieces. So there's very little organization in this embedding space. And we thought, well, what do we have to do such that this knowledge is actually organized in a predictable way, so that if you know you need a blue Lego piece that has a very particular shape, you know exactly where to go without having to touch and move every individual piece. And The way we did this, or the way we are working on this, is this Myriad project, where the idea is, how can we basically take unstructured medical and biomedical knowledge and actually structure it into a large database of millions of question-response pairs. And so we actually did that using, I don't want to go too much into the details, a pipeline of different filtering and quality control techniques to arrive at a large atlas of medical question-answer pairs, roughly 6 million. And we can take the same source knowledge and connect a language model either to this map or this atlas or to the source knowledge in the prior unstructured version. And we see that out of the box, without optimizing anything, usually when you see performance gains, someone has spent months and used many GPUs to train their model to get a few percentage points better. We basically only change the format of the data, and we, for free, get significant performance gains across various language model scales on some of the most challenging medical question answering benchmarks out there, for instance, MedExpert QA. And in the paper or the preprint, we also show that there's various other benefits we can get from this structured representation of knowledge. Well, so that's structure grounding. Let's go into the other part. I wanted to mention the process supervision. I notice now both of those sound actually super dry, but I think it is actually important to never trust a language model on its own. So I remember when ChatGPT came out, many people were super excited about it, and some of my colleagues and me back at Stanford then, we thought, well, I don't want it to hallucinate guidelines. I don't want it to hallucinate patient data. I want it to go, check exactly where the right information is, and come back and give me that. And for that, language models are actually quite good. They're not so good at, they're good at confabulating information, so we should not trust their parametric knowledge, but we need to actually hook it up to the right environment and to the right knowledge bases. So regarding the process supervision, what we here mean is we don't only need to optimize the way a language model is connected to knowledge sources. We also need to check exactly what is the language model doing. It is a black box, yes, but now we're entering this time of, or the era of reasoning models, where a model is not just directly producing an answer, but where a model is producing individual steps that then culminate in the answer. And those individual sub-steps, if it is a hard problem, a reasoning problem, we can actually check them. So this has been extremely successful in language models that are used for generating code and for language models that do mathematical proofs. But the problem with those two other domains is that the problems are very verifiable, which is actually a good band name, the more I think about it. And here we have a different situation. So the medical domain is not verifiable. You don't have individual statements that you can check. Does it compile like a piece of code? Or you cannot check, oh, are there certain axioms that are being violated? So what can we do? We didn't give up, I can tell you that. We thought, well, let's have some kind of actor critique setting where there's a base language model that makes a certain statement, and then there's another language model which takes this statement, and the only task of that model is to actually go into the literature, check guidelines and other knowledge sources, and then come back with a verdict whether this statement, in the context it knows, is correct or wrong. This is kind of an oversimplification, but I think for the purpose of this, I think it's enough. And so in this project, we then built this reward model. We call it a process reward model for medical reasoning. And what was really nice about this is we could show that after building this process reward model, you can actually just scale the effort, like the number of attempts that you give your language model for the same task. And if you do it more times, the performance will grow faster than if you use the previous standards, how this test time scaling has been done. And the nice thing about this reward model is that it is actually augmented with the literature. So it is kind of an agent that is going into the literature and checking guidelines for a specific question. And this is the green line here. And the bright green shows how the performance drops if you remove this retrieval component. What's also very interesting to us, at least, is those PRMs, they have been around in other domains like code or math. But there, if you develop a PRM, it only works for a very specific model, like the very specific Quen 3.5 at this scale. And we found that our PRM, we can just reuse it at inference time and just swap out the backbone to other models, and it would still improve performance. And I think this is really interesting because it introduces a new paradigm how we should use language models. So there is the hospital or the company that has its own secret knowledge bases, specific tooling, and then the newest language model that gets released every 2 weeks can just be connected to your own knowledge corpus via this paradigm, instead of having to retrain your model every time a new model comes out. There's also some follow-up work that we will present this summer in Seoul at ICML, also one of the leading AI conferences, which is trying to take this reward modeling paradigm one layer or one step forward, where you actually have some sort of, we call it process reward agent, that has multiple actions at disposal. So it can either just check a language model's reasoning step and directly give a score, whether it's good or bad, or it can pause and go into the literature, search, and then come back and does it real time. Previously, the previous models would do it only post hoc at the end of a generation, because that was much more efficient to do. But this model now does it real time. So if a language model is producing a step, it can immediately go and do this. And this unlocks a new capability, namely we can do beam search. So you could have a language model, here it's called Pi, the reasoner Pi. It's frozen, we don't train it. And this process reward agent can go and induce some sort of tree search over various hypotheses. And if you think about this, is very interesting for any sort of open-ended task, like diagnostic reasoning, where individual branches might be diagnosis, or this could be scientific research, where there's a bunch of hypotheses that might be conflicting. And this process reward agent helps us at each node in a reasoning process to get a score, how valuable is this? Or should we even roll out further or not? Great, so that was 2 flavors of how can we make AI agents more reliable in the general medical domain. And now that was kind of dry, I think. So now let's talk about more applications. And there specifically, I'm interested in faithfulness right now. In 2 months, I'm sure I'm interested in something else. But the application I wanted to mention here is the radiology, because we just had this workout. And why I'm talking about this, of all the applications, what we found in this paper was that if we build some sort of agent environment where an agent can use various types of image processing tools like segmentation models, it can select slices of a CT volume, we can use a different contrast and so on. Lots of image processing software, you would say, that previously a radiologist might have used or someone that analyzes the image. Now this agent can do it autonomously. And well, what was really interesting, this improved performance in automatically drafting reports, nice and all. But what was really interesting to me was that this increased the entropic faithfulness notion that they published a few months back from a value of 0 to 37%. And I've never in my entire career seen this before. Usually when you're measuring some sort of metric that you care about, it improves a bit if you work really hard. And somehow the baseline just got a flat 0. And now maybe I explain what faithfulness actually means. So faithfulness means if you give some sort of task. Here, for instance, you have a CT volume and you have a task like write a report about the CT volume. And faithfulness checks what happens if you give a hint. The hint could be either a true hint of a specific finding, like pulmonary embolism, that might be in the image, or it might be a false hint. It might be some hallucinated finding. So it can be a positive or a negative hint, and you just give it in the prompt. And now, if the model produces an answer that is different from if you don't give the hint, so it's kind of like a perturbation. You check whether there's a flip in the response if you give the hint versus not. And if you have a flip event, you then ask the model in a follow-up question, why did you change? And the model is faithful if it can say, I changed due to the hint. And if it is not able to explain why exactly and just points at the image and it talks about the evidence in the image, then it is not faithful. And this capability, previously we just had vision language models. So there was one state-of-the-art method, this 3D vision language model. If you use that, it in 0% of the cases was able to attribute this flip to the hint it received. So it doesn't really know why it makes its decision. It doesn't really have access to its internal reasoning. And the nice thing about our RAD agent is that it really could go there. And I mean, I can give you an example of how such a trace could look like. It will do many different types of tool calls, and it will select different types of slices and segmentations, etc., has a scratch pad where it writes down what findings are currently interesting, and then it will also remove some findings. And if in the end you have a report, you can actually backtrace exactly at which step something appeared or vanished again. And for such a system, it's much easier for the agent to actually go and introspect your own reasoning because you actually have it laid out like a map. So this is a very specific application I'm sure many of you will not care about, but I think the paradigm is important. We are going into a new direction with white boxing processes that previously were just one step. It's somehow coming out of a neural network. We don't know where is a prediction coming from. And now all of a sudden we have models that produce traces. And those traces might have links to the literature, to established knowledge. I think this is a really exciting new world we're entering. Okay, on that note, I get to my summary. I believe the medical domain is super exciting for AI, but it also remains very hard, even for foundation models. And I'm also convinced, not just because I'm in academia, that pure scaling, just throwing more data at bigger models, only gets us thus far, and we actually need to really work hard on new research to improve the reliability of those models. We have some preliminary evidence that external tools will help augment language models and multimodal language agents to make them more reliable, to actually embody them into contexts where they have not been previously, and this will improve multimodal reasoning capabilities of those systems. And ultimately, I also believe strongly that it matters how we represent knowledge it has to access. We already see that when you look at code repositories, or anywhere online, it feels there's a shift where a lot of the knowledge that has been prepared for humans prior now is being prepared and surfaced for AI agents. And the same way, I think we need to make sure that scientific knowledge is actually presented in a way that language models that need to reason about it actually best can best access it in a reliable manner. And ultimately, I also think we need to carefully check and never just freely trust anything a language model says. So we need to really check individual reasoning steps. And I think agents should actually do that too. Great. With that, I'm already at my end. Thank you so much. Happy to take questions if there's time.